Welcome to Last Minute Lecture. This free chapter overview is designed to help students review and understand key concepts. These summaries supplement, not replace, the original textbook and may not be redistributed or resold. For complete coverage, always consult the official text.
So in the year 1637, there was this French philosopher and mathematician, René Descartes, and he's just lying in bed staring up at this fly crawling across his ceiling.
Which, most people would just find incredibly annoying.
Right, I'd be looking for a rolled-up magazine. But Descartes, he actually has this massive revelation. He realizes that at any given moment, he could describe the exact, precise position of that fly using just two numbers.
Its distance from two adjacent walls.
Exactly. And in that single, seemingly totally mundane moment, he completely fused the two oldest branches of mathematics together. I mean, he took the ancient Greek world of pure geometry, so, shapes and lines and curves, and mashed it straight into the abstract numerical world of algebra.
Yeah, it is without a doubt one of the most profound paradigm shifts in human history. Because before that moment, geometry and algebra were just... they were completely different languages. They didn't speak to each other at all.
And Descartes basically built the translator.
He did, which we now call the Cartesian coordinate system.
Welcome to our deep dive. Today we are taking your textbook notes, your formulas, and your study guides on Chapter 3 of your pure mathematics coursebook, Coordinate Geometry. And we're looking at the mathematical DNA of, everything. From the GPS in your phone to, the orbits of comets. We are going to explore how abstract algebraic equations are translated into tangible visual reality.
And, this goes so far beyond just passing a math exam. The principles of coordinate geometry are the absolute backbone of modern engineering, of astronomy, of physics.
The real world.
Exactly. The exact same mathematical logic you use to find the center of a circle on a piece of graph paper, that's used to calculate the reflective properties of satellite dishes and deep space radio telescopes. Once you understand the mechanics under the hood here, you really start seeing the entire physical world as this series of beautifully predictable intersections.
Okay, so we're essentially building the blueprint of reality today. But before we can, design a satellite dish that listens to the cosmos, we need to understand the raw materials. And in this geometric universe, everything really just begins with the simplest possible action, right?
Right. Connecting two isolated points on a blank grid.
Yeah. So if you place 2 points anywhere on a Cartesian grid, let's just call them point A and point B, you instantly define a line segment.
Yes, and the moment you have a line segment, there are two primary physical properties you absolutely need to measure. You need its exact middle, and you need its total length.
And finding the midpoint, that actually feels incredibly intuitive. I mean, if I have one point at an x-coordinate of 2 and another at an x-coordinate of 8, the middle is just 5.
Because you're just finding the average.
Right, exactly.
That's really all it is. I mean, the midpoint formula in the textbook, it often looks like this formal, rigid piece of algebra, right? Like add the x values and divide by 2, then add the y values and divide by 2.
Yeah, 6 by 1, 1, plus 6 by 2 over 2.
Exactly. But conceptually, you are just calculating a center of mass. You are finding the exact point of balance between two extremes, horizontally and then vertically.
Okay, so that's the middle. But then there's the distance between those 2 points. And I remember first seeing the standard distance formula, and it's this massive, intimidating square root.
Oh, it looks terrifying.
Right. It's the square root of the difference in the x-coordinate squared plus the difference in the e-coordinate squared. But when you actually look closely at the architecture of that formula, it's just a very famous theorem wearing a disguise, isn't it?
It's Pythagoras. Pure and simple. The Cartesian coordinate system is essentially just an infinite grid of right-angled triangles.
Wait, that is such a crucial connection for people to grasp, because we aren't really measuring a diagonal line directly at all, are we?
No, almost never. In coordinate geometry, we measure strictly left to right and strictly up and down.
Right.
So if you want to know the distance between point A and point B, you imagine drawing a horizontal line straight across from A and a vertical line straight down from B.
And where they meet forms a perfect 90-degree corner.
Exactly. The difference in your x-coordinates, that's the horizontal base of that triangle. The difference in your e-coordinates is the vertical height and the diagonal distance you actually care about.
That's just the hypotenuse.
Yes. So the distance formula is quite literally just 80 total $80 plus b total 2 equals $2 out, rearranged to solve for Sadel.
Just take the square root of the whole thing. That's amazing. And the logic is so universally consistent, which means once you trust that logic, you can start really manipulating it.
Oh, absolutely.
Like, let's look at worked example 3.1 from the text. You won't always be asked to simply find the midpoint. Sometimes you're given the starting point, say point P is at -7, 4, and you're given the midpoint, which is 3/2, -11, and you have to find the mysterious endpoint, point Q.
Right. And, you could set up a whole algebraic equation to solve for the missing variables.
But you don't really have to, do you? Conceptually, you can just use the logic of walking.
Yes, the vector approach.
Yeah, like if I'm standing at a starting point -7 on the x-axis, and I walk to the midpoint at +1.5, well, I've just walked positive 8.5 units.
Right.
So to get to the end of the journey, point Q, I just walk another 8.5 units from that middle point, which lands me at an x-coordinate of 10.
Exactly. The mathematical shift from the start to the middle has to be completely identical to the mathematical shift from the middle to the end.
It's just applying a constant vector. So for the y-axis, if I go from 4 down to -11, that's a drop of 15. So I just drop another 15 from -11, and I'm at -26. Point Q is 10, -26.
It's a perfect way to visualize it.
Yeah.
Much faster than grinding through the algebra.
Okay, so speaking of constants, we've measured the length and the middle of our line segment, but we also need to measure its behavior, right? Like, how steep is it?
Well, that brings us to the gradient. Or, the slope. It's the ratio of vertical change to horizontal change.
The classic rise over run.
Exactly. It tells you exactly how your E variable responds to a change in your X variable.
And measuring that steepness is how we determine the relationship between different lines. Like, if two lines are perfectly parallel, think of train tracks that will never, ever intersect. Their gradients are identical. The steepness is exactly the same. $1 equals $2.
Right. But things get a bit weirder when lines collide at a perfect 90-degree angle, when they are perpendicular.
Yeah, the mathematical rule for perpendicular lines is that if you multiply their two gradients together, the result is always exactly -1.
Or, to put it another way, the gradient of the second line is the negative reciprocal of the first line.
See, I want to pause here for a second because this is a rule a lot of people just blindly memorize without understanding it. Why a negative reciprocal? I mean, why do we take the fraction, flip it completely upside down, and reverse the sign?
Well, think about the geometry of a physical 90-degree turn. Imagine a line that is climbing a steep hill. Let's say for every one step forward, it goes 4 steps up.
Okay, so the gradient is 4/1, just 4.
Right. Now, if you take that line and physically rotate it 90 degrees clockwise, what used to be your vertical height is now your horizontal distance. And what used to be your horizontal distance is now your vertical height.
Oh, wow. The axes literally just swap roles.
Exactly. So the rise becomes the run and the run becomes the rise. That's why we flip the fraction upside down.
That makes total sense. But what about the negative sign?
Well, because you rotated it, a line that was previously climbing upwards, a positive slope, is now pointing downwards. It has fundamentally changed direction. That is why the sign flips from positive to negative. The algebra is just a perfect reflection of the physical rotation.
That is so cool. And we can actually use this concept of gradients to prove things about physical space.
Oh, definitely.
Like worked example 3.4 brings up this idea of a road trip.
Yeah.
If you have 3 towns on a map, town A, town B, and town C, and you want to prove they all lie on the exact same straight, infinite highway, you just check their gradients.
In mathematics, we call points that sit on the exact same line collinear points.
Right? Collinear. And to prove points are collinear, you just have to prove that if you drive from town A to town B and then you just keep driving to town C, you never touch the steering wheel.
Right, you don't turn.
Exactly. The steepness from A to B must be perfectly equal to the steepness from B to C. You just set the gradients equal to each other and solve.
So we now have the tools to measure the distance and the steepness between specific points. But what if we want to capture that entire infinite highway in a single mathematical expression?
Right. We have to move from measuring finite line segments to writing equations that describe infinite straight lines.
The universal language of lines.
Yeah.
And depending on what kind of problem you're solving, the textbook actually gives you a toolbox with 3 different types of straight line equations.
Yeah, and let's unpack this toolbox because it can feel like overkill. First, there's the most famous one, yat equals excessa plus telever.
Right. Well, that is your visualization tool. The moment you look at it, it explicitly hands you the 2 most important visual characteristics of the line. The steepness, which is 1 to r, and the exact point where it crashes through the y-axis, which is the y-intercept.
So it's perfectly designed for graphing.
Exactly.
Okay, then you have the general form, which looks like x by l plus by I equals 0. And this one always feels a bit more opaque to me. I mean, it doesn't immediately tell you the slope.
It doesn't, no.
Yeah,
but it is incredibly neat. It's your organizational tool. The general form usually removes all the messy fractions and just sets everything equal to 0.
Right.
So when you are, say, writing computer algorithms to calculate intersections or dealing with complex geometry, having an equation without fractions that gathers all the variables on one side, it just makes the computational heavy lifting much, much easier.
Makes sense. And the third tool in the chapter is the point gradient form. $y minus $y equals times $6 minus $by.
Now, that is your builder's tool. It is functionally the most useful equation when you are actively trying to construct a line from scratch.
Because all it demands is one single coordinate point and a gradient.
Exactly. Just an anchor and a direction.
Let's actually put that builder's tool to work with worked example 3.8. Let's say we have two cell phone towers, tower A at -5, 1, and tower B at 7, -2. And we need to draw the exact boundary line that separates their territories perfectly in half.
So in geometry, finding that boundary is called finding the perpendicular bisector.
Which sounds like a massive, complex operation. But if we break it down into components using what we've learned, it's really just a checklist.
Absolutely. We are building a brand new line, so we need two things: a point to anchor it and a slope to dictate its direction.
So if we want to divide the territory perfectly in half, our anchor point has to be the exact midpoint between the two cell towers. We just average their coordinates. -5 plus 7 is 2, over 2 is 1, and 1 plus -2 is -1, over 2 is -0.5.
So your midpoint is 1, -0.5. Boom, we have our point.
Right, and we want this boundary to be a perpendicular bisector. So we first find the gradient between the two towers. Change in y is -3, change in x is 12, so the gradient is -1 over 4.
And then we apply that 90-degree rotation logic. We flip the fraction from 1 over 4 to 4 over 1, and we change the sign from negative to positive.
So our perpendicular gradient is just 4.
Instantly.
And then we just take that midpoint, 1, -0.5, and that new flipped gradient, 4, and we plug them straight into our builder's tool. Yeah minus -0.5 equals 4 times 6 minus 1 and 1. We didn't have to do any crazy geometric proofs. We just built it from spare parts.
It's highly modular. And, once you master straight lines, the natural mathematical progression is to bend them.
Yes.
We move from lines that go on forever in a constant direction to lines that curve.
And the most perfect curve in the universe is the circle. But how do we describe a circle algebraically? Because we can't really use rise over run when the steepness of a circle is constantly changing every millimeter you move along its edge.
Right. To understand the equation of a circle, you really have to change how you think about shapes. You can't think of a circle as a solid, hollow ring. You have to think of it as a strict set of rules.
What do you mean by rules?
A circle is the locus, or the mathematical path, of all points that obey one single command. Stay exactly the same distance away from a central anchor point.
Okay, I always visualize this as a dog tied to a pole in a massive grassy park. The pole is the center coordinate, which we can just call $, and the leash is our fixed distance, the radius.
I love that analogy.
Right, so if the dog pulls that leash taut and just runs all the way around the pole, the path its paws carve into the grass is our locus. It's our circle.
And that physical constraint, the taut leash, is the absolute key here. Because if you freeze the dog at any point on that circular path, you can draw a right-angled triangle connecting the dog back to the pole.
Wait, are you telling me that Pythagoras is hiding inside the circle equation too?
Oh, he absolutely is. The standard equation of a circle is 16 squared plus minus Boolean squared equals 2 squared. Does that structure look familiar?
Oh my goodness, it's just $1 is 2 plus $2 equals 2 and $2 again.
Precisely. The horizontal distance from the dog to the pole squared plus the vertical distance squared must always perfectly equal the length of the leash squared.
That's crazy.
The entire equation of a circle is literally just the Pythagorean theorem locked in a continuous 360-degree rotation.
That is genuinely beautiful, and that standard form is so clean. Like you look at 6 honors 5 squared plus minus 2 squared equals 9, and you know instantly. The anchor is at 5 and 2, and the leash is 3 units long because 3 squared is 9.
Yes, the standard form is perfect for visualization.
But in reality, coordinate geometry sometimes throws you a massive curveball. You don't always get the neat standard form. Sometimes you get the expanded general form, which looks like a completely random string of algebra. Sex 0 plus 2 barrow plus 2 barrels plus 2 y 0 plus 7 barrow equals 0.
It looks chaotic. the x variables and y variables are totally scattered, and the visual clarity of the center and the radius is completely destroyed.
It's just math soup. Like in worked example 3 tucks 12, they give us $6 2 plus 2 tries plus $10 minus 80 20 minus 40 equals 0. How do you find the dog in the pole when the equation looks like that?
Well, you use a structural realignment technique called completing the square.
Right, completing the square. And I know a lot of people view this as just like an arbitrary sequence of algebra steps you have to memorize to pass a test. But what are we actually doing geometrically when we complete the square?
Geometrically, you are reverse engineering the expansion. When the equation is scattered like that, the pure horizontal and vertical forces that define the circle's center are jumbled together with constants. So completing the square is the mathematical process of gathering all the horizontal x forces.
Yeah.
So the 6 tower 2 ordinance, the 10 tower there, identifying what's missing to make them a perfect square and basically forcing them back together.
So for $6 O plus $10 S, half of 10 is 5. So it's $6 plus 5 squared, which generates an extra 25.
Exactly. And then you do the exact same thing for the vertical y forces. Y is O minus $8 becomes the y plus x squared, which generates an extra 16.
But wait, you can't just magically add a 25 and a 16 to an equation just because you want it to look pretty.
You can, as long as you balance the scales. Whatever phantom numbers you conjure into existence to complete the perfect squares on the left side, you must instantly add to the other side of the equal sign.
Okay, so you move the original negative 40 to the right side, so it's positive 40. Then you add the 25 from the x's and the 16 from the y's. 40 plus 25 plus 16 is 81.
Yes.
So you're essentially gathering up all the scattered pieces, forcing them back into those neat little Pythagorean brackets, and whatever numerical debris is left over on the other side of the equal sign simply becomes your radius squared.
Exactly. So your equation is now 6 Balaclus squared plus c minus 4 squared equals 81.
Which means the center is negative 5, 4, and the radius is 9. You pull the hidden center back into focus.
It is deeply satisfying when you do it right. And once you have your circles clearly defined, there are a few golden geometric rules you really need in your toolkit.
The right angle facts.
Right. These are properties that are universally true for every circle in existence, and they almost always involve, you guessed it, right angles.
Pythagoras really is the VIP of this deep dive. So what are the rules?
First, if you draw a triangle inside a semicircle, meaning one side of the triangle is the full straight diameter of the circle, and the opposite point touches the edge anywhere on the curve.
Okay.
That angle at the edge will always, without fail, be a perfect 90-degree right angle.
Wait, it doesn't matter where on the curve the point is.
It doesn't matter at all. As long as it spans the diameter, it will always be 90 degrees.
That's wild. Okay, what's rule 2?
Second, if you draw a chord, which is just a line segment slicing across the circle from one edge to another, and then you draw a line from the center of the circle perfectly perpendicular to that chord, it will always slice that chord into 2 exact equal halves.
Oh, so it acts as a perfect bisector.
Yes. And finally, the tangent rule. A tangent is a straight line that flies past the circle, grazing the outside edge at one single microscopic point of contact.
Right.
If you draw a radius from the center of the circle to that exact point of contact, the radius and the tangent will meet at a perfect 90-degree angle every single time.
So we have our rules, we have our universal equations for straight lines, and we have the Pythagorean equations for our circles. We know exactly how they behave in isolation, but the real physical world isn't isolated, is it?
No, things crash into each other all the time.
Which brings us to the grand finale of this chapter and our deep dive, the intersections of lines and circles.
This is where we literally crash algebra and geometry together. If you want to find out where a straight line and a circle intersect on a graph, you have to solve their equations simultaneously.
Okay, mechanically, what does that actually look like for a student doing the work?
You usually take the simpler linear equation, say y equals $2 plus 1 app, and you physically substitute that expression into the circle's equation every single time you see a y.
You are mathematically forcing the two shapes to share the exact same reality.
Yes. And because the circle's equation has squared terms, when you force that straight line into it and multiply everything out, you are always going to generate a quadratic equation.
Right. Something in the form of xad2 plus xa2 plus 6 equals $.
Always. And solving that quadratic equation will give you the exact coordinates of the collision. But here is the brilliant shortcut. You don't actually always have to solve the entire equation to understand the nature of the collision.
You can just use the radar.
Exactly. You can use a built-in radar system called the discriminant.
The discriminant. That's the 2b tunnel minus 4 color part of the quadratic formula, right? Like the chunk that lives underneath the square root symbol.
That's the one. That little piece of algebra dictates everything. Before you do the heavy lifting of finding the exact coordinates, you just run the numbers through pp2 minus 4 sur x. The result basically gives you three possible realities for your line and your circle.
Okay, let's walk through those realities. What happens if I calculate the discriminant and I get a positive number, say positive 16?
If it's a positive number, it means your quadratic will yield two distinct real solutions. Geometrically, this means your straight line is acting as a secant.
A secant.
Yeah. It is behaving like a skewer passing through an apple. It pierces the circle's boundary, travels through the interior, and exits out the other side, hitting the circumference at two distinct points.
Got it. It creates a chord inside the circle.
Okay, reality number 2.
What if the discriminant isn't positive, but lands exactly, perfectly, on 0?
If the discriminant is exactly 0, the plus or minus part of the quadratic formula just vanishes. You only have one single repeated solution.
Wait, if there's only one solution, it only touches the circle once. But geometrically, how does an infinite straight line touch a round circle exactly once without actually going inside it?
It'd have to be a tangent.
Oh!
It perfectly grazes the outer boundary, making contact with a single coordinate before just continuing on its path.
The gentle grazing! I love that! Which leaves reality number 3. What if I calculate 2b2 minus 4 in dollars and I get a negative number? Say, negative 5.
Well, if the discriminant is negative, you are asking the quadratic formula to take the square root of a negative number.
Which totally breaks the rules of real numbers. I mean, you can't multiply a number by itself and get a negative.
Precisely. In the realm of real numbers, there is no solution. And geometrically, no solution means no collision. The straight line completely misses the circle.
They exist on the same Cartesian plane, but they never, ever interact.
The radar tells you you're in the clear.
That is just a brilliant way to conceptualize the algebra. It's not just random rules. Let's kind of zoom out for a second and look at the progression we've just traveled.
Quite a journey.
Yeah, we started with Descartes looking at a fly, realizing we could map reality using just 2 numbers on a grid. We learned how to find the midpoint and then measure the distance between those points using Pythagoras in disguise.
Right.
We discovered how gradients dictate steepness and how flipping them creates perpendicular rotations. We built equations from scratch to capture infinite straight lines. We tethered points to a fixed center to carve out circles, completing the square to uncover their hidden coordinates.
And finally, we crashed those equations together, using the discriminant to predict whether a line would skewer the circle, graze it, or miss it entirely. It is an incredibly tight logical progression. It's not just a collection of random formulas you memorize for a test. It's a cohesive language. And as we said at the start, this language is the blueprint. Yeah. When an aerospace engineer is calculating whether a piece of orbital debris is going to completely miss a satellite or graze its solar panel or punch straight through the hull, they are running the exact mathematical logic of intersections and discriminants that we just discussed today.
It's the literal mapping of the universe.
It is. But I actually want to leave you with one final thought to explore on your own.
Oh, please do.
We've spent this entire deep dive confined to a flat, two-dimensional piece of paper. X-axis and a y-axis.
Right. Everything is completely flat.
But the universe isn't flat. So here is the mind-bending leap for you to ponder. What happens to this exact same algebra when you pull these shapes out of the paper and into the third dimension?
You add a z-axis.
Exactly. Yep. Suddenly your flat circle equation inflates into a three-dimensional sphere. A curving parabola becomes a sweeping paraboloid, which is the exact shape of a satellite dish. The coordinate geometry we master today isn't the end of the journey. It is merely the flat foundation for understanding the three-dimensional geometry of the entire cosmos.
From a fly on a ceiling to the architecture of the solar system, that is just incredible. Well, a huge thank you for joining us on this deep dive. The next time you open a mapping app on your phone or look up at a satellite dish on a roof, remember, there is a hidden, beautiful layer of algebra and geometry operating beneath it all. The map isn't just a picture, it's a living calculation. From the Last Minute Lecture team, keep questioning, keep exploring, and we'll see you on the next deep dive.